The ideal op-amp model and solving strategies. A real op-amp device is quite complicated. Inside. And to deal with it is well beyond the scope of this course. And let me just show you what the device looks like. This is the op-amp. And you can see how it has a non-inverting, it has the output, it has all of these other things that we're seeing here. So because we can't solve this, we will use the ideal op-amp model. And when I talk about this, you're going to see that I'm going to define this as just as the ideal model for short, which is a calculational model to get values. So let's write it down. It's fairly simple to write down. So here we go. The ideal op-amp model. So the first thing here is that the input terminal currents are 0. In other words, I1 is equal to I2 is equal to 0. What this is really telling us is that an op-amp draws no current into either input. And the second one is that the node voltages at the inputs are equal. In other words, V1 is the same as V2. That is, an op-amp will do anything it can to its output to ensure that its two inputs have the same voltage. This is the role of the negative feedback line. So let's add a picture to this so you could visualize what it is that I'm talking about. So my op amp looks like this. And so I have minus, plus. Then the idea here is that when I look at these guys, what am I seeing? One, either of these terminals, remember this is terminal V1, this has no current flowing into that node. Just like this one, this has no current flowing into that wire right there. Then the second one tells us that V1 and V2 must be exactly the same. And that's gotta be pretty tricky. And so when you look at this, because we remember that this is A, the gain, times Vn, but Vn is V1 minus V2. And again, I should be careful here is that all of these are always relative to some ground someplace. This is the model. So I want to box this because this is an important one. So that's the model that we really want to go after right here, and you will be an expert at it by the time this. So let me make a remark, okay? And this remark, oops, forgot an R there, is to try to give you a sense of what this means. Okay, the fact that no current flows in or out of the input terminals implies a high input resistance slash impedance. It's really impedance. So when I'm looking at my op amp model, here's the thing that I would be thinking about. So I'm going to have to draw this big. And let's say I come all the way over to here. So when I'm looking at this, if I have an input terminal right here, when I'm looking inside, why is it that the current is 0? Well, because this guy here has a high internal resistance or impedance. And again, this is minus plus, of course, we're talking about Vn here. And there is a second piece to this, is that when you're looking at this as a dependent source, you're finding that this guy, so if this is truly a dependent source, note that there is some resistance right here, but it has to be really low. So this is a low output resistance slash impedance. So very little is dropped so that that dependent source is really what the output is. So I think that this model here is a good picture of the ideal model to sort of visualize it this way. So now what we want to look at is we want to look at the problem solving strategies. And what we should think about is that there are two approaches to solving op amp circuits. And of course, we have to use the ideal model. The first one is node analysis. The second one, I'm going to say, is simple circuits. So let's start with the node analysis. So when you apply node analysis, there's a lot of caution that you want to think about. And I would say that node analysis is by far the most common way that people solve it. That doesn't mean it's the best, but let's look at node analysis here. So the first step, we've typically have done counting, and we should continue to do the counting, but I'm going to assume that we've already practiced node analysis quite a bit. So in the first step, what you want to do is you want to determine the output voltage V out in terms of the input. The input voltages of Vn being the difference between V1 and V2. Using standard node analysis. And the thing that I'm going to say right here is that this causes problems. So I'm going to say caution here. And the caution says, do not write a node equation for V out. So this is pretty important. So let's look at this in pictures here. So one has to be careful in determining what is a node voltage in op amps. And that seems kind of silly because you're an expert at node analysis. So node voltages are different from the source voltage in a voltage controlled voltage source. So let's look at this thing. So suppose we have a dependent source. So suppose we have a voltage controlled voltage source. And in this case, I'm going to say that when I look at this, I'm going to have something like this. And I'm going to say that in this situation, I'm going to have V out is going to equal to 4 V in. Now we know what V in is. It depends on two nodes. So if you look at the first nodes, right, there's a negative and there's the positive. So I'm going to come in here and I'm going to say, okay, so then this guy is V1, this one is V2. So I would say that this guy, these are node voltages. V1 and V2 are node voltages. V out is not a node voltage, but the source value. You cannot write an equation for V out because it depends on V1 and V2. So if you go and you look at this at an op amp, so we could then say that for an op amp, one cannot write a node equation for V out, even though it appears to be a node voltage. Even though it appears that way. So what I mean by that is that now, if I translate into this language, now I have minus and plus. Right? We know that this guy right here is then going to be V1, V2. And then when you look at this guy, you look at this guy and you're going like, hey, this is V out. And this guy, of course, is for V in. In other words, one cannot write a node equation for V out. Note that I'm repeating myself, right? I'm repeating myself because in the beginning, it's real easy to make that mistake. Now, let's go to step 2. So if you go to step 2, so then I'm going to say, this is super important again. After setting up the node equations, apply the ideal model conditions to the node equations. What you're going to find out is that you're going to have too many unknowns. And so by looking at the ideal conditions of I1 equals to I2 equals to 0 and V1 equals to V2, you're going to find out that you're going to be able to now have equal amount of equations and equal amount of unknowns. So now if I go to step 3, we then determine V out and I out. And the practice here is that I out, the sign convention is that it flows into that. And so then, we want to determine V out and V in for the op amp. Now, I want to make a side note to be clear on why we can't use mesh and loop. So mesh / loop analysis cannot be used on op amps. And of course, the question is, why? The supply inputs, so the input supplies which are not shown supply current to the op amp. Since one does not know these incoming currents, one cannot account for all of the currents in the circuit. This immediately voids mesh and loop analysis for op amps. Node does not require knowledge of the currents because it calculates node voltages. Therefore, it's valid to use it. So that's node analysis right there. So now let's go to the next one. The next one is what I call the simple circuit approach. And by the way, this is my preferred method. And here we go. So if I look at the first step, one immediately applies the ideal conditions, the ideal model conditions. and determines the effects of I1 equal to I2 equal to 0 on the op-amp circuit. And then the second step, we then follow the current flow. In the circuit and continuously apply Ohm's law. One will be quite surprised how much op-amp intuition one gains using this approach.